dissolve salt in hot water and cold water? You may observe that you can dissolve more salt in hot water than cold water. That means an increase in temperature or heating can increase solubility, right? Do you know why? In this video, we will discuss enthalpies for different types of reactions during which you will get answers for this observation. Let us start our discussion with the standard enthalpy of combustion. Combustion is the process of burning a compound in the presence of excess oxygen. The standard enthalpy of combustion is the enthalpy change per mole of a substance when it undergoes combustion such that all the reactants and products are in their standard states at the specified temperature. For example, during the complete combustion of 1 mole of butane, 2658 kJ of heat is released. Hence, the standard enthalpy of combustion of butane is minus 2658 kJ per mole. As heat is evolved during combustion, you may say that combustion is an exothermic process. Now, let us look at the enthalpy of atomization. The enthalpy change accompanying the complete dissociation of 1 mole of substance into gaseous atoms is called the standard enthalpy of atomization. For example, the enthalpy of atomization for 1 mole of dihydrogen is 435 kJ per mole. Here, the enthalpy of atomization is also the bond dissociation enthalpy. To understand this more clearly, we may understand the concept of bond enthalpy. Consider chemical reactions in general. Chemical reactions always involve the breaking and making of chemical bonds. Energy is required to break a bond and energy is released when a bond is formed. The enthalpy changes associated with chemical bonds can be expressed in terms of bond dissociation enthalpy and mean bond enthalpy. We may discuss this with reference to diatomic and polyatomic molecules. For example, consider breaking 1 mole of dihydrogen gas into hydrogen atoms. The enthalpy change 435 kJ per mole involved in this process is the bond dissociation enthalpy of hydrogen-hydrogen bond. Note that it is the same as the enthalpy of atomization of dihydrogen. And this is true for all diatomic molecules. Thus, for diatomic molecules, bond dissociation enthalpy is the enthalpy change when 1 mole of covalent bond of a gaseous covalent compound is broken to form products in the gas phase. However, in the case of polyatomic molecules, bond dissociation enthalpy is different for different bonds within the same molecule. For instance, the enthalpy of atomization of methane is 1665 kJ per mole. Although all 4 carbon-hydrogen bonds in the methane are identical in bond length and energy, the energies required to break the individual carbon-hydrogen bonds differ. You may add these energies together to get the total energy required, that is 1665 kJ per mole. In such cases, we may use the term mean bond enthalpy. Hence, the mean carbon-hydrogen bond enthalpy in methane is 416 kJ per mole. In fact, bond enthalpies of the reactants and products may be related to the standard enthalpy of a reaction. And this is valid when all the reactants and products in the reaction are in their gaseous state. Next, let us understand lattice enthalpy. The lattice enthalpy of an ionic compound is the enthalpy change that occurs when 1 mole of an ionic compound dissociates into its ions in the gaseous state. However, it is impossible to determine lattice enthalpies directly by experiment. Hence, an indirect method called Born-Haber cycle can be used to obtain lattice enthalpy. We may understand the steps involved in Born-Haber cycle with an example. Consider the conversion of 1 mole of solid NaCl to gaseous Na plus ions and Cl minus ions. Here, firstly, solid sodium changes to gaseous Na. The enthalpy of sublimation for this step is 108.4 kJ per mole. In the next step, gaseous Na ions are ionized to give sodium ions. The ionization enthalpy for this step is 496 kJ per mole. Similarly, dissociation of chlorine takes place. The enthalpy of dissociation of chlorine is 121 kJ per mole. This is followed by chlorine atoms accepting 1 electron and changing into chloride ions. The electron gain enthalpy for this step is minus 348.6 kJ per mole. Finally, the gaseous ions combine to form solid NaCl. The enthalpy change involved in this step is called lattice enthalpy. If you see the schematic representation of cycle, it may be realized that the sum of the enthalpy changes round a cycle is 0. Then you may obtain the lattice enthalpy as shown here, that is 788 kJ per mole. Next, we may discuss one of the applications of lattice enthalpy. In this context, we may first understand the enthalpy of solution. The enthalpy of solution of a substance is the enthalpy change when 1 mole of it dissolves in a specified amount of solvent. For example, when an ionic compound dissolves in a solvent, of course, enthalpy change occurs. In addition, you may also observe that the ions leave their ordered positions on the crystal lattice. These ions are free in the solution and solvation of these ions occur. If the solvent is water, then you may say hydration rather than solvation. Thus, if you consider the whole process diagrammatically, you may obtain the enthalpy of solution from the selective values of the lattice enthalpy and enthalpy of hydration of ions. For most of the ionic compounds, the enthalpy of the solution is positive and the dissociation process is endothermic. Therefore, the solubility of most salts in water increases with rise in temperature. Finally, we may discuss the enthalpy of dilution. To understand this, consider the enthalpy change for dissolving 1 mole of gaseous hydrogen chloride in 10 mole of water. Now, in this case, if you consider a series of enthalpy changes, you may represent the enthalpy changes as shown here. As more and more solvent is used, the enthalpy of the solution approaches a limiting value, that is, value in an infinitely dilute solution. Now, if you subtract the first equation from the second equation, you will get delta H is equal to minus 0.76 kJ per mole. And this value is called the enthalpy of dilution. Hence, you may say the enthalpy of dilution is the heat withdrawn from the surroundings when an additional solvent is added to the solution. Now, I have a question for you. What happens when we heat an iron rod at one end? We heat one end of an iron rod. After some time, its other end will also become hot. You can see the flow of heat is unidirectional from higher temperature to lower temperature. How will you explain this spontaneous heat flow? We will discuss this in our next video. Now, let us summarize what we have learnt.
Manorama Horizon. Learning made simple.